Hi, I'm Hibner-Koblitz, and this is a video abstract of the paper Elliptic Curve Cryptography, the Serpentine course of a paradigm shift, by Neal Koblitz, Alfred Menezes, and me. One of the goals of this paper is to recount some of the twists and turns in the history of ECC as it emerged as a favored technology for public key cryptography. This paper is in part a case study of the social construction of technology. Although such factors as gender, race, class, nationality, or global politics often influence the development of technology, they do not seem to be relevant to the history of public key crypto. It's surprising that gender has played no discernible role, since the popular history of cryptography is tied up with the military and is full of male-dominated stories of intrigue. Rather, the social factors are professional and institutional in nature. For example, certain high-prestige terms such as science and mathematical proof acquire their own dynamic as people become invested in a certain narrative. The force of this narrative can be great even when the evidence fails to support it. This is called narrative inversion. Our examination of the history of ECC offers no support to those who would argue that technology follows an inevitable path that is independent of social constraints.
We examined the history of elliptic curve cryptography against the backdrop of what we call the ideal model, which is the image that cryptographers hope to project to the outside world. The central feature of this model is survival of the fittest, the notion that it is only the intrinsic merits that determine which technology wins out. One way to see how far this ideal model is from the reality is by asking some what-if type questions. For example, think of how different the history of pairing-based cryptography would have been if it had been proposed, say, 4 years earlier, in 1997, when ECC Central on the RSA website was warning of the dangers of ECC, rather than in 2001, when a consensus in favor of ECC had already formed in the research community. If pairing-based crypto had come on the scene during the height of the ECC versus RSA rivalry, the ECC skeptics would have refused to allow people to sweep under the rug the fact that pairing-based crypto uses precisely the types of curves that a few years before had been considered to be insecure, namely elliptic curves whose group embeds in the multiplicative group of a small degree extension of the ground field. Some people would have hoped that by undermining confidence in pairing-based crypto, they might have been able to bring down all of ECC with it. But because of the particular chronology, exactly the opposite happened, and both ECC and pairing-based crypto have nearly universal acceptance.
In our paper, we use isogenies to show that under certain circumstances, it might be safer to choose a very special elliptic curve than one with random coefficients. This flies in the face of conventional wisdom on parameter selection. One example in the paper is the following. In 2000, NIST recommended two elliptic curves over the field of 2 to the power of 571 elements for the highest level of security. One of them, denoted K571, is an anomalous binary curve that has significant efficiency advantages. The other, denoted B571, has randomly generated coefficients and is generally assumed to be more conservative of the two choices. However, suppose that on a very small but not negligible fraction epsilon of the curves over this field, the discrete log problem could be attacked by some new faster than square root algorithm. And suppose that the property of being a weak curve is independent of isogeny and endomorphism class. In this hypothetical scenario, we use random low-degree isogeny walks between curves to show that B571 is less secure than K571. This is the opposite of what most people would expect. The conclusion is not that K571 is preferable to B571, but rather that such choices are really a judgment call. This shows once again that cryptography is as much an art as a science.